porridge. But after the porridge, we made our way to Mars. And I think we're discussing how Mars has changed over time. So this is one of my favorite pictures because you can see how the surface liquid water carved itself into Mars' surface long ago. Mars lacks plate tectonics, so what we see on the surface today is actually way back in Mars history as well. In fact, today Mars' atmosphere is too cold and too thin to sustain surface liquid water. And so this tells us that the atmosphere must have changed drastically over time. So what could have warmed early Mars? In the early 1990s, folks investigated this question first with just a simple greenhouse model of if you have a lot of CO2 in your atmosphere, is that enough to warm it? And the answer was no. And then they went to clouds and volcanism and lots of theories until finally they went back to the 1 or 2 bar approach, but added a little bit of hydrogen into your atmosphere. And they found that when hydrogen collides with CO2, it induces a transient dipole moment in that exact time that it collides. And so those collisions, even with just a fractional amount of hydrogen, maybe 5 or 10%, can cause enough warming to sustain water in a 1 bar atmosphere. So my project asks, where did that hydrogen come from? And also, did Mars' evolution affect its climate and chemistry over time? And hint, these may be related. So to get at this question, I developed a photochemical model that's coupled to a 1D climate model. Kinetics is the chemical model, and it starts with CO2 and water in the atmosphere. That CO2 can become photolyzed to form CO, and usually photolysis of water will produce HOX, which will cycle you back. Once you have the photolysis of water, you can also form hydrogen near the ground, which is where a lot of the water is, because that's where it's warm. And that hydrogen can then diffuse up and then escape. So my model considers all of that, and it also considers 2 different ground approaches. So first we consider a cold and dry epoch, where maybe it was cold and icy and you didn't have liquid water. In that case, the crust, which might have had reduced iron at the time, is exposed to the oxidized atmosphere, and you can start to draw down oxidants into the ground. In the other epoch, we assume that it's warm and wet, with surface liquid water flowing. And in that case, the water will react with that reduced iron and suck down OH, but that frees the hydrogen, and the hydrogen can go into your atmosphere. So I'll investigate the chemistry in both of these approaches at steady state, which means for a long time, waiting for the chemistry to go into balance. So in warm climates, we find that the crustal hydration rate, which we vary in different line styles, drastically changes the amount of hydrogen, which is not too surprising. The hydrogen has a chemical lifetime of about 10 to the 5 years, so it takes a long time for that hydrogen to build up. But once it does, large amounts of hydrogen, which are plotted in blue, do cause a very warm surface temperature, which is plotted up here. And so these are the varied rates of crustal hydration, where no hydration means that all the hydrogen here is produced just from that water photolysis chemistry. Whereas over here, you can tell the crustal hydration is dominating the profile. We also plot the CO and O2 profiles, but the main takeaway here is the hydrogen and temperature. We also investigate the chemistry in cold climates, where in this case, I'm not plotting the temperature because everything is in fact quite cold, below 230 Kelvin. I added a new profile, which is this green line of CO2. And that's because in the previous case, the background atmosphere was dominated by CO2. But in this case, the photolysis of CO2 becomes unbalanced with that recycling reaction. When you start to draw down oxidants, such as O2 into the ground, that depletes the system of OH, which is one of the most powerful atmospheric oxidants. And so this reaction here becomes very slow. And so we find that Mars' atmosphere might have turned from CO2 towards a CO atmosphere on very long time scales of greater than 10 to the 7 years. So this work found 2 steady state solutions, a warm CO2 atmosphere with lots of hydrogen, and then a cold atmosphere transitioning from CO2 maybe over to CO. And the goal of my proposed work is to discuss if there's evidence for one or both. So a couple of years ago, my new advisor, Professor Robin Wordsworth, published this paper that actually ignored the chemistry that I presented, but instead asked if you just pump in these gases like hydrogen and methane into a CO2 atmosphere, how does that affect the climate on short time scales? Again, importantly, ignoring the time scale that hydrogen would need to build up. So in this work, they found that the alternating redox cycles of either reduced or more oxidized atmospheres does drastically change the climate. And so I hope to couple my model with his to investigate whether you can do this on such short time scales, because as I noted before, it takes hydrogen about 10 to the 5 years to build up. But that's important that the alternating redox cycles are important for this warming. In my model, I found that you can only keep Mars warm for a cumulative amount of about 2 by 10 to the 7 years. But during the Noachian, that's about 1/40th of the full duration of the Noachian. So we know it could not have always been warm. And so these alternations are important for explaining that warm climate it's sometimes. Getting back to the idea of alternating redox cycles, this was a table that I compiled from all of the published literature in which the MSL rover was roaming around the ground and scooped up soil samples, and it would take them into its oven and heat them up to find out what gases were in that soil. So all across the surface, we find things that are both oxidized and reduced on the surface. And so my proposed work is to take the results that I've already found, of the oxidized and reduced climates, and try to predict whether these things can form in different types of climate scenarios. I'm expecting that the oxidized ones will form mostly in those CO2 atmospheres, and the reduced ones might favor the more hydrogen-rich or even CO-dominated climates. Importantly, my photochemical model has been applied before to explain the surface deposits of the nitrates. So this was a work I published a few years ago where we found that the upper amount of nitrate that my model could predict roughly matched the lower limit of the MSL model results, which is this dashed line here. It's important to note that we did also find reduced things in an oxidized climate, which might go against my hypothesis. So there's kind of two things at play here. This was a bit higher than the nitrate, not because it's being rained out faster, it's actually orders of magnitude slower, but because the loss mechanism of nitrate, which is photoreduction, was much, much faster than the loss mechanism I assumed of cyanide, which was just hydrolysis. But in reality, both might be lost to reactions with iron, but the reaction rate coefficients for that are poorly constrained. So I ignored that in both scenarios. In the interest of time, I'm going to skip this one and get back to this, which is my proposed work, again, is to try to explain the formation of these in those different climates. Hopefully appealing to more of the astronomers in the room, you might be asking, why Mars at all? You're more interested in exoplanets. And so first, as I've made clear, I hope to better understand Mars atmospheric evolution. But that's really interesting because the evolution might influence Mars' early habitability. The idea of alternating redox cycles put the surface in disequilibrium, which is really favorable to life. Importantly, Mars is a great example of some of these smaller planets that you guys might find and observe. And so better understanding how it evolved will maybe help inform the exoplanet community about how those worlds are changing. So that's the end of my talk, and I'll take questions. Thank you.
Questions? All right. Time for review.
I'm not sure. A great talk, first of all, very interesting. You don't have to justify marks for me, but I'm interested in whether or not you were taking into consideration the idea that early Mars might have had a very extended hydrogen-rich atmosphere. I think Mars is sort of that border, right, where we expect that to be true mass-wise. And how that sort of changes the paradigm of this free hydrogen. Is that a really short-lived, photo-evaporated state, or Yeah,
that's a great question. A lot of the rocky planets in the solar system might have started out with very rich hydrogen envelopes, but they would have been lost very quickly before the 4 billion year old point. And so the interesting point of the Mars geochemistry that I'm discussing is 3.7 to 4.1, so just after that point, and it's more of a secondary atmosphere.
All right, any more questions? Maybe the next speaker could come on as well.
As an exoplanet astronomer that is very interested in Mars, this is really, really great research. I'm curious about the astrobiological implications of this, especially because we know the history of the Earth's evolution, that climate changes that have taken place over many, many millions of years have influenced the development of life. So how do you think this partial Noachian period where the radical change having hydrogen to removing it could have affected the development of life on the early Mars?
That's a great question. I would argue that there's pros and cons. For example, in the oxidized climate, you form more nitrates, which are helpful to early metabolisms, but possibly in the more reduced climates, you'll form more HCN, which is important to forming proteins. Again, that disequilibrium on the surface is also considered favorable to the early metabolisms. So it could go either way, but it's also important to notice that the change in climate means that the life would have had a shorter amount of time to form or evolve. So kind of pros and cons, and I would point to Mike Long, who's the astrobiologist in the room, to continue the discussion.
One more quick question. All right, that's all. Thank our speaker again.
Thank you.
Don't want to mess this up. Does it work? Cool. Okay.
Okay, all right, so now we'll hear from Jon Zink about hot Jupiters. All right.
Hi, everyone. For those of you I haven't met, I'm Jon Zink, and I work on exoplanet demographics. Today, I'm going to talk about hot Jupiters, and particularly whether or not they are low. So why do we care about hot Jupiters? They're this really strange class of planets. They're roughly Jupiter-sized, and they habit this weird part of parameter space between 1 and 10 days orbiting their host star. So they're extremely hot planets, and they obviously don't have any solar system analog. So why do we care, right? Like, they're not in the solar system, who cares? But they're such an important class of planets because they're so abundant. We have so many of them, and we can really learn a lot about atmospheres and all kinds of different features of dynamics with hot Jupiters. So they're a really exciting class of planets. Just to kind of further this point of why hot Jupiters are so strange, if we look at some of the demographics from hot Jupiters compared to the other 3 classes of planets, being super-Earths, sub-Neptunes, and sub-Saturns, we see this interesting trend in hot Jupiters, that they don't seem to change very much as you go across planet classes or stellar classes. While most of the other planet classes seem to decline in occurrence as you go to these hotter, more massive stars. It's not totally clear what the mechanism for that is, but somehow the hot Jupiters are a little bit different than all the other planet classes. So what do we know about hot Jupiters? The truth is, we don't know how they form. We have several different mechanisms, and I'm going to go over 4 today. These are kind of the leading 4, but by no means is this a fully exhaustive list of possible ways you could form a hot Jupiter. The first one is really straightforward. This is in situ formation. You basically just form it. It forms in place to some kind of, accretion mechanism at a very, very short period. There's enough material on the disk to coalesce and form this hot, very large planet nearby the host star. A secondary mechanism that's very popular is called coplanar high eccentricity migration. And the way that this mechanism works is you have 2 planets out beyond the ice line that are formed through some process, and dynamically those 2 planets interact and cause the inner one to have a large eccentricity, and then eventually you dump a bunch of the angular momentum through tidal dissipation onto the host star, causing this Jovian planet to migrate inward into a circular, very tight orbit. Another mechanism is secular chaos. It's a very similar mechanism to the coplanar high eccentricity migration. The big difference is now you have more planets in the outer cold region. So basically, high eccentricity migration with more and more planets really just adding to the chaos and causing the circularization mechanism to occur. And the 4th one I want to talk about today is light-off quasi-cycling. And this is an interesting mechanism where you have some offset between these 2 planets, the cold Jupiter and the soon-to-be hot Jupiter. And there's this quasi-cycling where you're exchanging eccentricity and inclination. And this weird exchange occurs where you drive up the eccentricity of the inner guy to near unity. Then tidal dissipation occurs. So you end up with a hot Jupiter. So these are kind of the 4 main pathways that exist. There's obviously more, but these are the 4 we're going to focus on today. So exoplanet demographics, what we were hoping to do is look at a sample and see if we can back out any constraining features in the existing hot Jupiter sample and see if we can kind of identify which one of these models might work better than the others. So we're looking at a homogeneous RV sample here. This comes from the California Legacy Survey. There's 719 planets, and it goes out to almost out to 30 AU. So it's a very, very wide-reaching sample, and it's probably the most complete homogeneous sample of RV planets we have. Inside of that sample, there are 127 planets that we were kind of focusing on in this giant regime, 11 of which are hot Jupiters and 46 which are warm cold Jupiter systems. So we're kind of going to split the sample right at the 10-day period line, saying the purple guys are warm cold Jupiters, and below 10 days, everything else is a hot Jupiter. Within that sample, we had a few other interesting features. So 5 of the hot Jupiter systems had an outer companion, and 11 of the warm cold Jupiters also had a companion. So right away, this makes you wonder, is there some kind of interesting companionship occurrence feature? And it looks like there is. Companionship is very, very common for hot Jupiters. And we thought, kind of going into this study that we would find some heightened companionship rate for the hot Jupiters versus the warm cold Jupiters. But we did not. We found that they were basically identical. Both systems seem to favor multiplicity in giant planets. So if there's a giant planet, there's a very good chance there's another giant planet somewhere out in the distant part of that system. So multiplicity is ubiquitous. That's the big takeaway there. So that wasn't necessarily interesting, right? It didn't tell us anything specifically unique about hot Jupiter systems. Maybe there's some kind of architectural feature that we can look at in these systems. We wanted to look at the mass ratios. So now we're looking at mass ratios of warm cold Jupiter systems versus hot Jupiter systems. Looking at the warm cold Jupiters, if we just do a simple, mass outer divided by mass inner, on average, we find that warm cold Jupiter systems are about 1. So this appears to be a random draw. There's no preference for any type of mass organization in these warm cold Jupiter systems. Now, what was really exciting when we started digging into this is that there is a clear and very strong feature in the hot Jupiter sample. It seems to be that hot Jupiters favor a much, much larger, much more massive outer companion by a factor of about 3. So this is, we've accounted for completeness and all the other features that could potentially bring this about, but it seems like this is a really strong signal. And there's something in nature that's requiring this 3 mass outer companion, 3 times more massive outer companion in the hot Jupiter systems. So on its surface right away, you might be thinking maybe there's some dynamics at play that are kind of causing the rise of these hot Jupiter systems. So we dug a little bit deeper just to see if there was anything else we could squeeze out of this sample. And we found that, we wanted to look at the eccentricity, right? Eccentricity is another marker for some kind of unique dynamics that might be at play giving rise to these hot Jupiter systems. So looking at the warm cold Jupiter population, we were able to extract some distribution for the eccentricity of the outer companions. And when we look at the hot Jupiter outer companions, we see that they are on average, more eccentric than the non-hot Jupiter systems. So this seems to indicate that there's some kind of dynamic relic here that we're seeing, which is definitely an expectation of some of these formation mechanisms. So let's go back to our 4 formation mechanisms that I kind of stated off at the beginning. We have in situ, coplanar high eccentricity migration, secular chaos, and Kozai oscillations. And these are kind of the different features that I've talked about today. Is 2 giant planet multiplicity is common. 3x mass companion in the outskirts is very important for hot Jupiters. And an enhanced eccentricity component in the companions we also identified. The 4th column, which I haven't talked about, is the obliquity distribution. And so the obliquity distribution, we didn't really look at in our study, but just to give you guys a background, the obliquity distribution is basically how aligned with the spin axis these planetary systems are. And for the most part, in the literature, it's been found that the obliquity of hot Jupiter seems to be peaked near 0. So there tends to be a preference towards an aligned spin axis, meaning that there's likely not some large inclination offset that might arise in the formation of these hot Jupiter systems. So what's the breakdown when we apply all of these constraints to the different models? we can see that there seems to be one model that kind of across the board is green all the way. And that's this coplanar high eccentricity model. It seems to match up with all the findings from our demographic sample, 2 giant multiplicity. So we can throw out secular chaos with that one because we didn't find like numerous multiples in the outskirts of the systems. The 3x mass companion, enhanced eccentricity companion, and the obliquity distribution all align with coplanar high eccentricity migration. This is a really exciting finding because it seems to be zeroing in on one particular formation mechanism for the formation of hot Jupiters. I should caveat this by saying not every single hot Jupiter system forms this way. It just seems like this is the most dominant mechanism for forming hot Jupiter systems. Unfortunately, this is like probably the most vanilla version of forming a hot Jupiter, right? Like coplanar high eccentricity migration. Kozai had this cool offset, secular chaos. Chaos is just a cool word, right? Like who doesn't want it to be secular chaos? And in situ is interesting because like it's weird, you have to have a really massive disk. So a little bit disappointing that it's not a cooler mechanism, but you find what you find. And so in conclusion, I'll just kind of go over the summary of our finding. Hot Jupiters tend to have an outer companion, but so do most systems that have a giant. That companion tends to be 3 times more massive. At least 3 times more massive, I should say. There's systems where it's much more massive. Hot Jupiters have their outer companion tends to be more eccentric, indicating there's some dynamics at play there. And finally, we conclude that high eccentricity migration seems to be the dominant mechanism for the formation of hot Jupiters. So with that, I will conclude and take any questions. Thank you guys for listening.
Right, lots of questions. Okay, sometimes.
Nice work, John.
Thanks.
I have a question about the demographics part. Am I crazy, or is there like a gap at around 30 days that splits that population into 2? Is that real?
Yeah, that is real. So there's this weird like warm Jupiter class that is really strange and people don't understand it yet, how it forms. It seems to be maybe like a in-between state between forming a hot Jupiter and not forming a hot Jupiter, but it's really unclear. There's a lot of work to be done there. Yeah.
Thanks.
All right, more questions?
Other than that, I asked a lot of questions. I'm curious if you guys are working on creating any constraints on the mechanism by looking at planets in extremely young systems, like in star forming regions that are 1 million, 3 million years old, and whether or not the orbital architectures can help you understand the percentage of time when mechanisms at play.
Yeah, that's definitely something we're looking at. It's hard to do with this RV sample because the RV sample is like a very particular patch of the sky. It doesn't have very many young clusters in it. But with transit surveys, we can kind of get a better sense of that. That's something we're thinking about with like K2 and TESS and Kepler, potentially Roman in the future.
All right, I think we're out of time now. Let's thank our speaker again.
Good.
Testing. Okay.
All right, so we're going to hear from Marc Hon now about returning back to the theme of planetary engulfment, but now we're going to hear about a great escape. So why don't you take it away?
Thank you. Well, before lunch, we talked about. Do we now? All right, thanks. So before lunch, we talked about doomsday scenarios and the death of planets. Well, I'll talk to you about a planet that has seemingly cheated death. So before I begin, I'd just like to assert that the TESS Space Telescope, it's finding for planets, but at the same time, it's also observing stars across the entire sky It's allowing us to do some very fabulous astroseismology across the entire sky. So on the bottom left here, this is basically a heat map of the masses and therefore ages of stars across the entire sky. And this is allowing us to identify some truly interesting candidates, some truly interesting systems, which includes the exoplanet host that I'll talk about today, 8 Ursa Norris, or 8 Uni. This is a 1.5 solar mass red giant, has a near solar metallicity, and in past years, astronomers has discovered using RVs the presence of a Jovian planet, 1.5 Jupiter mass, orbiting at a distance of only 0.5 AU from this giant star. So at a first glance, this might seem like a run-of-the-mill planet facing engulfment. So I'll just run the scenario down with you. So as stars evolve past the main sequence, as previously described, they evolve up into red giants, and they will achieve a maximum size based on our understanding of stellar evolution. And if you have a star that is in the midst of expanding to its maximum size, and a poor planet whose orbital distance is smaller than the maximum size of this star, then eventually, as the star evolves, it will grow larger than the size, than the distance of its planet, and it will engulf and destroy this particular planet. And because of this, we don't expect any planets in tight orbits around stars in more evolved evolutionary phases, such as in the red clump. So, due to this scenario, it came as a surprise to us. But before I get there, because we don't actually expect any close-in planets around the red clump, we have previously looked at planets around host stars. And this is a function of the evolutionary state. You can just focus on the red point because it's kind of blocked by the logo there. But the lack of any close-in planets around giants from previous RV surveys has been interpreted as evidence that planets don't survive the evolution of their host stars up the giant branch. Which is why it came as a surprise to us when we looked at the astroseismology of 8 Uni, to find out that it is in fact in the core helium burning phase. So on the left here, these are the oscillation spectra of your expanding red giant branch star on the top left. And on the bottom left, this is what we would typically expect for a star that's already burning helium in the red clump. And what you see for 8 Uni here matches exactly the oscillation spectrum of what we would expect for a core helium burning star. So the great discovery that test astroseismology has allowed us to achieve or understand about this system is that this particular star is burning core helium. So let's unpack what this actually means. It means that the star has already once evolved up to a maximum size of 0.7 AU, which is much larger than the distance of its current planet, which is 0.46 AU. So this means at some point, the planet must have been embedded within the envelope of the star, presumably, because right now the star is in the red clump. It has shrunken down, but it was once this very big. So how did this planet actually survive throughout this perilous process? Before we got ahead of ourselves, we wanted to confirm that the planet was real. So what you see here, these are archival RV measurements. These were from the discovery paper in 2015, and we followed this up with some of our own from Keck Observatory over the past year. And what you notice is that we can pretty much get the same period and the same near zero eccentricity of the system, which implies a stability of RVs over 12.5 years or 50 cycles. And this is a good sign because we would expect RV stability from an actual planet rather than stellar activity mimicking RV signals. On top of that, we wanted to do our due diligence, and we also looked at more indicators in whether or not the star could cause this RV signal that we're seeing. And we looked at photometry, spectroscopy, spectropolarimetry, and all of these seem to indicate that the star is quiet. There are no signs of activity that could mimic an RV signal that is of a 90-day period, which is the period of this particular planet. So at this point, we have the onus is upon us to describe how this planet could actually survive. There are a few schools of thought. The first could be common envelope evolution. Could the planet would have somehow survived being embedded within the envelope as the star evolved up the giant branch? And we don't think that's possible due to a massive difference in timescale. The evolution of a star that is expanding up the giant branch would be much longer compared to the time taken for an embedded planet to in-spiral into the star and just be destroyed. And we calculate this simply by the ram pressure in the envelope. What is the time taken for ram pressure to decay the orbit of the planet into the star itself? Now, there's a dependence on mass here. So you might think, okay, if you have a very dense object like a brown dwarf, could it have withstood in the engulfing process altogether? And it turns out that this is limited mainly by observations from Gaia as well as the RVs. Well, RVs strongly disfavor a very massive object, or 99% it's not going to be, more massive or like a brown dwarf mass. And Gaia Rui also rules out anything like a red dwarf that is fairly massive. So this rules out something that is very massive that could have withstood this whole engulfing process. And on top of that, based on energy considerations, we made some simple calculations and found out that if you were to take something that is engulfed at the tip of the red giant branch and bring it down to 0.5 AU, you can't impart any energy to actually dissipate the envelope of the star itself. So that's why we don't believe common envelope evolution actually happened for this system. Now, the second school of thought could be as some of the scenarios for hot Jupiter, as was previously mentioned. What if the particular planet existed from much farther out, but tidal dissipation occurred during the tip of the red giant branch when the star was at its biggest, which eventually decayed the orbit of the planet all the way down to its current distance. Now, the idea is not very favored due to how difficult it is to have such a migration occur. Here, these are different models of the trajectory of the planet, and at the bottom here, you see the radius of the star as it went to the tip of the red giant branch. And in most scenarios, you see that the planet survives being pushed much farther out, or just plunges right into the surface of the star and it doesn't survive. It's extremely difficult to have something that survives by dipping down all the way to 0.5 AU. And due to this, we actually disfavor this particular scenario of tidal orbital decay. Now, alternatively, you could think of a high eccentricity tidal migration. What happens is that something much farther out perturb this planet, which may have been farther out, into a close-in orbit that eventually circularized as it got close to the host star as it is today. And the problem with this particular scenario is the time scale. At a distance of 0.5 AU, this particular planet is roughly 10 times larger in distance than your average hot Jupiter. And the tidal circularization timescale is extremely sensitive to the separation between the star and the planet. So we made some calculations, and as you can see here, that regardless of whatever mass you use, it's the circularization timescale is going to be much longer than the Hubble time. So we don't believe that this planet could have actually circularized from a much more distant orbit itself. So at this point, we're running out of ideas. We weren't quite sure what to actually think of trying to explain this system. But here's a tip for anyone doing stellar evolution. If your star is extremely weird, you should start asking, is it in a binary? Has it been a binary? So it turns out that there are simulations that show that a merger between a red giant and a white dwarf could actually prematurely make the expanding red giant go into the core helium burning phase, or the red clump phase. And the very same simulations also show that you could actually create a resulting clump star that is very rich in lithium. So what happens is that as the white dwarf sinks into the core of the red giant star, it triggers a series of flashes that quickly burn trigger the lithium production process that gets transported out to the exterior. So why am I bringing up lithium? Melinda has talked a bit about lithium earlier, and it turns out that this particular star is very overabundant in lithium, is roughly 10 to 100 times more abundant in lithium compared to stars at its same evolution and at the same mass itself. So combined with this information, we could be looking at something that was once a red giant white dwarf pair. Now, do we see these kinds of systems out there? It turns out that we do. These are called ELCVN binaries. These comprise a red giant orbiting a white dwarf at a very short period, less than 10 days. And we ran some simulations to just simulate what would happen if you were to place a roughly unequal mass ratio binary around them. And we could find that you could in fact have such a system that evolves into an ELCVN type binary while having a planet that is somewhat stable around these two stars itself. So the planet that we see today might have been a circumbinary planet in the past, and these two stars eventually form a red giant white dwarf pair that's sort of merged together itself. Now, there is one final hypothesis that we posit here. It is a bit more speculative in nature, I would say. And it is the idea that the planet never existed from the beginning, but the merger of the red giant and the white dwarf itself, as shown here, produced a debris disk that formed something similar to a protoplanetary disk from which this planet eventually emerged. And this idea is speculative because it's been difficult to provide observational evidence of this, but there's been floated about that this could have been a second generation planet. So first generation planet would have been around from the beginning. A second generation planet would have been formed through some interaction between binary processes itself. So I would just like to say Hala, which is actually the name of the planet that I did not introduce earlier, it has a formal name, is the first time they've actually confirmed a close-in planet around a core helium-burning star. And this particular discovery has shown us that very evolved stars can host close-in planetary systems. And it could suggest that binarity plays a role in the extended survival of these very forbidden systems or very exotic systems itself. And so since Melinda threw a New York Times article earlier, I just thought I'd reciprocate with one of my own. All right. So I'll end my talk here with just an outline of the scenarios that could have produced this close-in planet around this star. Thank you.
Okay.
Hey, that was a wonderful talk. So I'm not a third person, but one thing that I do remember from astrophysics was that wait for giant star binaries sometimes create type 1a supernovae. So why does that not happen when the two stars emerge?
I think it depends a lot on the mass, the mass of the both components itself. In this case, the progenitor mass is not sufficiently massive, I presume, to produce something that would result in a supernova.
Okay, thank you.
Hi, Mark, really nice talk and the discovery. I think the whole star has a is a Hipparcos source, and I just checked that the Hipparcos and Gaia astrometry seems to have a pretty noticeable difference. So will the astrometric acceleration somehow help to constrain the planet mass orbit or the binary scenario?
So there is some amount of acceleration seen between the Hipparcos and the Gaia era, but then the signal to noise is fairly low. But we have noticed that there could be evidence of a very long period companion in the system based on also our RV monitoring and also the Gaia Hipparcos acceleration. So that would be interesting to follow up. We should definitely keep monitoring this.
All right, let's have the next speaker come up quickly.
Regarding the lithium overall numbers that you saw in your spectra, so in this scenario where you have a giant companion and a wide dwarf, the wide dwarf might be accreting material via fed material from a giant companion, and this could cause nova eruption on the wide dwarf surface, which produce the most lithium in the universe actually. So could this be, I'm like, this is a very naive question and really unrelated to what you're doing, but could this lithium overabundance coming from some sort of eruptions of the companion surface? And this is posing the need because we see a lot of lithium nova system. Michael, I think, thought that this might lead to type 1a supernova. It's very unlikely to happen, but nova could very much happen in such system.
Yeah, I've heard about the presence of lithium in novae itself. I'm not quite sure how that would fit into, a binary scenario, because imagine that the star would have to reform at some point. I'm not sure. If the novae produces lithium, how does that lithium get into the star? That's not quite clear to me. Yeah, we could talk more about this. Thanks.
All right, let's thank our speaker once again.
Oh, okay. Good. Do they see it online?
Yeah.
I don't know. Yeah.
It's not sharing.
It's not sure.
Usually it's about that, it's a feature.
Yeah. Is it shared now in live?
Looks like it.
Okay,
Okay.
great. All right, now we'll hear from Jake Turner. We're gonna be talking about, he's gonna be talking about exoplanetary magnetic fields.
Okay, thank you very much. Oh, yes, so I'm gonna ask the question, what about magnetic fields? I'm gonna tell you all about it. So we jump right, okay. So I first would like to just take a step back and what we know about other substellar magnetic fields. So if you look at our solar system, magnetic fields seem very ubiquitous. So all planets had or have had magnetic fields sometime in their lifetimes. Venus, there's a question mark, but some people think that it may have actually had a magnetic field. And so that's the case for big planets as well as small planets, as well as moons. So Ganymede also has a magnetic field currently. We also think the moon used to have a magnetic field. And I show like a figure here of some of the magnetic field structures, which are all very diverse and very interesting in their own right. So it seems like it's a very ubiquitous thing. And then if you look to brown dwarfs, they also seem to have magnetic fields. And that's been detected since almost 20 years ago now, actually here at Harvard. And also, so because of that, a lot of people have been thinking for a long time that exoplanets should have magnetic fields as well. And people have been searching for many decades. But you might be asking, why do we even care? Care about atmospheres, care about all these other things. Why do we care about magnetic fields? So the main reason is if you detect the magnetic field, you know there's a dynamo in the interior, and you can actually learn something about the interior structure of the planet that way. We actually did this in the solar system in the 1950s for Jupiter for the first time before we even sent spacecraft there. And eventually the Voyager missions did that for Saturn, Uranus, and Neptune. And so we were actually able to learn very interesting things about their interior that we otherwise couldn't do that unless we sent a probe there. And the probes actually confirmed what we found from the magnetic field observations, as well as dynamics. So this is good for exoplanets because really all we really know about exoplanets is their mass and radius, and there's a lot of degeneracy. So if we can get another elements into what their interiors are like, that'd be really good to understand their formation and their evolution. As well as currently, we actually think if you have a magnetic field in your planet, especially for hotter planets, that will actually dynamically interact with the atmosphere and actually cause atmospheric effects that otherwise would not be there. So hotspot offsets, stuff like that. So that's actually really important if you care about the atmosphere and how they evolve. Some people care about stars. And so if you have a really close and hot Jupiter, it can actually magnetically interact with your star and cause what we call star-planet interactions and actually cause things on your star that otherwise wouldn't be there. For example, star spots or flares, stuff like that. So if you care about stars, maybe you got to care about the magnetic field of the planet, as well as formation. So it's a really cool schematic showing how we think planets form and the magnetic field. If it has a magnetic field, will interact with basically all the stuff around it, and that might cause a difference in formation. For example, like how fast it rotates, or vice versa. That's not obviously not the only thing that you should care about. Atmospheric escape seems to be really important for the solar system. For example, this is actually a real simulation of Mars with real data on it showing this atmosphere escaping. It doesn't have a magnetic field. This is becoming more complex because it might actually depend on what your magnetic field strength is compared to the size and mass of your planet. And it might actually increase escape or decrease escape. So it's actually really important to know what the magnetic field strength is. But again, for Earth-like planets, it's definitely something interesting to know, as well as habitability. So it can be both from the atmospheric escape standpoint, as well as how the interior interacts with the atmosphere and interacts with the interior of the planet. For example, like plate tectonics could help you in habitability. So there's many reasons we should care. So how do we actually detect them? So there was a review article many years ago trying to figure out what are some of the techniques that you can detect them with. There's many techniques out there. Most of them are quite complex and difficult to actually try to get your head around. And so they determined that one of the best methods was radio observations, auroral observations, which I'm going to be talking about at most of the talk today. And then recently there was another technique of looking at high resolution helium polarized
light. If you look at the individual spectral line, you follow it as it orbits around the planet, you might actually be able to constrain the magnetic field that way. So those are the two techniques I'll be talking about today. There's a bunch of other techniques, and I've also worked on some of the false positives in my PhD on that. So what are we exactly detecting when we talk about radio observations? And so basically, we're actually seeing the stellar wind interacting with the magnetic field of the planet, and basically follow the magnetic field lines, and it gyrates the magnetic field lines. It's actually Jupiter radio emission there, and you see, and it actually creates the radio waves. So the electrons are following the magnetic field lines, and then eventually it also creates the optical and near UV aurora that we see. So it's all kind of connected. So what we're actually observing is electron cyclotron major emission. So then an electron in a magnetic field gyrating around creates radio emission. And if you can see that radio emission and you see a spectrum, basically the maximum frequency you see tells you what the polar magnetic field strength is. So you can right away get what the magnetic field of planet is. And it's a very simple formula here for the gyro frequency. So if we see the emission, we know what the magnetic field strength is. The good thing about this emission is it's 100% cyclically polarized, which is really nice. Not a lot of things are in the universe. You also expect the flux from the planet to be way greater than the flux of the star. We see that in our solar system. Jupiter is orders of magnitude brighter at 20 megahertz than the sun, as well as beamed. So if we're looking at one of these hot Jupiter systems that's tidally locked, some part of the orbit is going to be pointing towards us, some part is going to be away. So it's going to be like a lighthouse. So we actually have to observe the entire orbit to figure out what part is beamed towards or away from us. Okay, so people have been looking for this for a very long time. I think the first reference was 1977. So quite many decades. So I'm not the only one to think about this. Almost every radio telescope has looked either blindly or at known systems, especially once we started discovering exoplanets. And obviously I'm in here too. And the tentative detection I'll talk about that I've been talking about for the past few years was with LOFAR. And so it's very interesting. That's what I'm following up in my talk today. So this was the detection I talked about several years ago at my first Hubble Symposium, where we had where we looked at this system Tau Boo B, which is kind of cut off up there. Tau Boo B, the big hot Jupiter system, orbits a star in several days. And we saw both basically slow emission, basically emission that was over the entire 4 hours of our observation. And I show the on versus on beams there, and you can kind of see the emission pop up right away, right? So the off beams that are pointed at random sky are very different than the on beam, which is pointed at our target. If we just assume random Gaussian statistics, that was an 8.6 sigma detection, which was quite exciting. And then we also saw that there was burst emission. So it was actually really bright spikes. Like every second it's really bright, it goes away, gets really bright, gets away. We did the same thing, compare the off beams to the on beams, and we see that there's some difference there. That was unfortunately only a 3.2 sigma. So if we use those, we got a magnetic field strength of the planet between 5.5 and 11 Gauss, which was actually quite comparable to Jupiter, of 0.94 the magnetic moment of Jupiter, which was quite exciting. However, in the paper and in the discussion, we said we really need to confirm this, because again, this was only one orbit. We actually did not observe multiple orbits, so that's what we've been trying to do for the past few years. And then in a paper last year, we actually tried to look back at the original data, the original orbits that we looked at, and tried to actually solve all of the things you need to solve in terms of where the beam would be pointing towards or away from us. And we actually found something quite cool. So this is the orbital phase of the planet, longitude of the planet itself. The blue line is where the radio emission is coming from. And then the green line is actually where Earth intersects that. We're thinking either way, Earth or the planet. And where those intersect should be where there's emission. We actually saw emission basically where the intersections were at, a phase of 0.65, phase of 0.8, coming from two different poles. So that was quite exciting. So that was in a paper last year. And last year I talked about our multi-site campaign that we're trying to use telescopes from all around the world, LOFAR in the Netherlands, NHFP in France, UTR2 in Ukraine, and LWA in New Mexico. And unfortunately, most of the data was not available at the time. Only LOFAR was interesting, but we actually looked back at some of the NNUFAR data and was able to extract something from it, which is nice. So NNUFAR has been undergoing commissioning for the past 2 years. And has anybody here has ever worked on a new instrument? Anything that can go wrong has gone wrong. So it definitely has been a whirlwind of a telescope. But it's quite cool. It's right in the middle of France. There's from 10 to 8 megahertz. It has about 96 arrays. You can see some of them up there. And it's more sensitive than LOFAR, so it's quite a good telescope in that respect. But it has a lot of problems with this new. And this is what I presented last year, where we actually have a non-detection. So we observed the system once, we saw it, we observed it again, 3 years apart. We don't see anything. We were quite confused on why we didn't see anything. But one of the causes was possibly stellar variability. And so that's the thing that we've been looking at for this past year. So we've been using NHFR to basically observe the system as many times as possible throughout 2 times its magnetic cycle. So Tau Boo is a really interesting star because it actually has 120-day magnetic cycle. That's very quick compared to the sun. But luckily for us, we can observe over that entire cycle and try to get some interesting results. And so that's what we've been doing. So we've been observing at the both interesting phases almost every few weeks, as well as every other phase, just kind of get baselines of what's going on to make sure that we know what's going on, basically. And that's what we've been doing. And we also get simultaneous magnetic maps of the star from some of our colleagues. They're still working on that, so we don't have results of that today. But this is fresh off the computer, so to speak. I did this like a week ago, and we possibly have a redetection. So this is quite exciting. It's exactly the same phase we saw before, phase 0.65. And it's the time it's in the bursting emission, again, looks exactly like Jupiter. This is way more than a 5 sigma detection, which is quite exciting. But there's a lot of systematics in the telescope that we don't quite understand. So I'm not quite saying this is a detection just yet, but it definitely is interesting, that something to look forward to. And then in the future, we want to go to the moon. Because a lot of this is going to basically help us there. So one thing I didn't mention is that the only planets we can observe from the ground are Jupiter-like planets. So if we want to study anything else that's not Jupiter, the magnetic fields, we have to go to space, because the ionosphere actually blocks the light from there. And so one of the missions I'm involved in is called Roseless. It's actually going to be launched within the next few months, basically. And so these are some of the observation timescales we're looking at between November and January. We basically want to have Jupiter, Earth, and the Sun all in there. So Roseless is going to be on the near side. So we're actually going to look at Jupiter and Earth in the radio. They're doing other cosmology things as well. And I want to simulate those as exoplanets to see how many dipoles do we need to put on the moon to actually detect exoplanets, because that's what we're going to do next, where we want to put either one big array in a big crater of a lunar crater radio telescope, or we want to put a bunch of arrays called far side. And so I'm hoping that what we do in the next few months will inform these missions that can actually study Earth-like planets, magnetic fields. And then just briefly over the high resolution observations. So there, as I said, there was a study saying that you can use this to constrain the magnetic fields. And so we've been doing some more modeling showing that you actually need to do all the Stokes parameters actually to constrain not only the strength of the magnetic field, but its orientation. So whether the pole is pointing towards you or away from you, vice versa. And so it seems like we need all the Stokes parameters to do that. Thankfully, we've now done that. So we've observed this conical hot Jupiter HT19733b and all Stokes parameters. So, okay, my time is up. So we observed 2 in Stokes Q, 1 in Stokes U, and 1 in Stokes V. We see nothing, so just random noise, basically, which is actually a good thing because there's not a lot of systematics in the instruments. And this is the first time all Stokes parameters have been observed in transit. So thank you very much.
Right, any questions?
Okay. Are you able to put any constraints on the magnetic field strength of the HT189 with those?
Yeah, we probably put a constraint below like 1,000 gauss, which is not very good constraint, but it's the first constraint with this. We don't actually have that modeling yet. Antonia has been on sabbatical. Yeah, she's been on a sabbatical. So hopefully in the new year we'll have actually real models to compare to our observations. But
cool, that was it.
Yeah.
One more.
On the lunar crater radio telescope,
Yeah.
very excited about that potential. Is seismic activity, moonquakes are a really big deal for precision, but I know these are large wavelengths. Maybe this is not a problem. Does that pose any concern for, really putting together something like this?
We don't think so, because again, the wavelengths are the size of this room. So yeah, it's definitely something that you like. If it just moves a little bit, it's not that big of a deal. Thanks.
All right, let's thank our speaker again.
Thank you.
Yeah, and very
Testing. Are we sharing, right? Or are we sharing? Yeah, looks like. Okay, everything looks good on Zoom. Great, awesome.
All right, so we're gonna be hearing from Guðmundur Stefánsson, close in Neptune, orbiting an ultra cool star. All right, take it away.
Thank you. I'm just gonna see if we can hide that. Hide floating. Awesome. Yeah, thank you so much. Yeah, hello everyone. My name is Guðmundur Stefánsson, and I'm a second fellow at Princeton University. Although I'll be moving to a new faculty position starting in the beginning of next year at the University of Amsterdam. I want to take the opportunity to thank the conference organizers for a really great meeting so far, and also the leads on the program, Jon, Paul, and Andy. Thank you so much for the support and help. I really appreciated it. And now on to the science. I'm excited to talk to you about a new discovery of a surprisingly massive planet around a surprisingly small star. So let's dive in. So why do we care about detecting planets around small stars? So in the exoplanet community, we often talk about the M-dwarf planet opportunity, because there are really many reasons why detecting planets around M-stars or low-mass stars is really exciting. The first one is that M-stars are low-mass stars. They have masses from about 0.6 down to 0.1 solar masses, like I'm showing over there. And they're also intrinsically faint. This then moves the habitable zone, then the region around the star where liquid water could be sustained on the surface of the planet, closer in. And this increases the many different detection amplitudes, including radial velocity semi-amplitudes, transit depths are deeper, making it easier to detect smaller planets in and around the habitable zone. Another reason why M-dwarfs are really exciting is to detect planets, because M-dwarfs are numerous. M-dwarfs are the most numerous type of stars in the galaxy, but about 70% of the stars in the Milky Way are M-stars. And I like highlighting that also over here, because they are so numerous. That also means that they are also nearest neighbors. Here I'm showing the census of stars within in the stellar neighborhood within 10 parsecs from the recons team, showing over here that M-dwarfs completely dominate the stellar neighborhood. So if we want to understand planets and around the most nearby stars, which are going to be the most amenable for detailed characterizations, that means that we need to understand planets around low-mass stars. Last but not least, M-stars are known to host many planets, and actually they host more planets on average than hotter stars. Here I'm showing the planet occurrence rate, and planets per star as a function of stellar effective temperature, specifically here occurrence rates for small planets in close-in orbits. And as we go to cooler stars, the occurrence rate increases steeply. However, as you see over there on the left, is that the uncertainties on the planet occurrence rates, especially on the very lowest mass stars, could still need more work. And this is then primarily because the very lowest mass stars are intrinsically faint, and we need highly sensitive instruments that are sensitive, especially at near infrared wavelengths, where the SCD of M stars really peaks. So what does the planet population around M stars actually look like? Let's take a look. Here I'm showing the planet masses, or planets that have masses as a function of stellar effective temperature around M stars, highlighting in particular then planets with masses around very low mass stars, often also called ultra-cool stars, here in red. There are currently 3 systems known with masses, called TRAPPIST-1, T-Current star, and TJ 1061. You don't really need to remember the names of these systems, but the main thing that I want to highlight over here is that all of these systems are these compact networks of small terrestrial planets. And because there are so few systems known down over here, the question still remains, are these systems representative of the full sample of planets, or can they support formation of other types of planetary systems and architectures? And that's one of the main goals of the Hubble Zone Planet Finder survey, which I'm deeply embedded in or leading the observations of, is to really probe the planet population around the very lowest mass stars. So what is HPF? HPF stands for the Hubble Zone Planet Finder, which is a near-infrared spectrograph on the 10-meter Hubble telescope in Texas over here. We designed SPF to be a near-infrared high-resolution spectrograph to push down on the RV precision down to 1 meter per second, really pushing down on what had been done with near-infrared detectors and technologies. And to really capitalize on the brightness of M stars in the near-infrared, we designed it to be a near-infrared instrument, has a wavelength from 810 to 1280 nanometers at a resolution of about 55,000. And with HPF, we've been carrying out a long-term survey, surveying 40 nearby mid to late M stars within 25 parsecs to probe the planet populations around these stars. Here I'm showing an expected sort of yield of the survey from a simulation in the minimum mass orbital period plane, highlighting a nominal habitable zone around the ultra-cool star there in green. We expect to detect about a dozen planets at more than pi sigma, and about a double of that in that is our lower significance. That's highlighted then with the blue points and the white points, respectively. Some of these systems would then be within range and detection capabilities of upcoming instruments with the 30-meter class telescopes to obtain direct images and spectra of these non-transiting planets, which would be really exciting to take a look at once those are online. And we're excited to mention that the HPF survey is starting to detect some really exciting systems. The first one being LHS 3154b, which I'll talk about in the coming slides. So let's take a look at what the data looks like. Here I'm showing the radial velocities in top, showing clear radial velocity variations as a function of time over about 2 years. The lower left plot shows then a periodogram, revealing a clear peak at 3.7 days. Phase folding of the radial velocity curve over there on the lower right, showing a semi-amplitude of 23 meters per second. This then reveals a Neptune orbiting an ultra-cool star. The host star is really low in mass. It only has a mass of 11% of the mass of the sun. And it's very nearby at only a distance of about 16 parsecs. So where does LHS 3154b land on the previous plot? This is where it lands. It's an order of magnitude more massive than any of the other planetary systems known. And it's actually raising a number of different questions about how such a planet might actually have formed. Because expectations from planet formation theory really expect that the very lowest mass stars, which have lower protoplanetary disk dust masses, should only be compatible with forming than these one Earth mass planets. In this context, it's useful to talk about the planet to star mass ratio, which I'm showing over here, showing the planet to star mass ratio as a function of over period, specifically for then planets around ultra cool stars. LHS 3154b is over there highlighted in red, the highest mass ratio in close in orbits. So how might this planet actually have formed? So there are a couple of main different formation scenarios that we considered in our paper that we have currently submitted. One of them is core accretion and gravitational instability. Both of these were briefly touched on then during the cool talks yesterday. And so I'll only very briefly go through these. So in the core accretion scenario, then planets are forming in a protoplanetary disk, which has a gas component and a dust component. There are these planetesimals that form. Those are then planetesimals that have characteristic radii of maybe 1 kilometer or so. They're able to start to accrete, then the surrounding gas and dust, they can interact with each other, maybe collide, maybe eject a planet outside of the system, and eventually a fully formed then system remains with maybe many planets, maybe just a single planet. The expectation from core accretion theory around the lowest mass stars is that the outcome really predicts these TRAPPIST-1-like systems, these compact networks of terrestrial mass planets. And in the very extreme cases, they can only form maximum masses of about 5 Earth masses. So that's core accretion. For the gravitational instability scenario, that requires much more massive disks. Then the scenario there is that both the gas and the dust disk masses are much higher, and then that actually so massive that they start to collapse according to their own self-gravity. This is then more sort of along the lines of how brown dwarfs and stars actually form. And the scenario there is that this scenario can help explain the formation of massive gas giants at very distant orbital periods. And so that's the main expectation there. So our planet, though, LHS 3154b, is somewhere in between. It's a Neptune in a very close-in orbit. So in our paper, we primarily considered the core accretion scenario and ran a number of different planet formation simulations to see what parameters do we need to change around so that we can actually start to form this exciting planet. So we ran a number of different planet formation scenarios within the core accretion scenario. Here I'm showing the output of those simulations in the planet mass orbital distance plane, highlighting close-in Neptunes. They're in the gray box, and LHS 3154b is highlighted with the orange triangle over there. So we ran a number of different simulations, initialized then these protoplanets within a protoplanetary disk. There was a gas disk dust mass, both a gas component and a dust component, and we evolved that with time, did that about a few thousand times. The blue points over there then shows the output of those simulations, assuming then dust disk masses that are consistent with the observations that from protoplanetary disk observations from ALMA. In one of these cases, we were able to form a planet like that. There are, of course, a number of different parameters that go into these types of models, but in our testing, the main key parameter was indeed the total dust disk mass that is available. That also somewhat makes intuitive sense because that sort of really sets the scale of what are the building blocks that the planets can build out from. You can start to build the cores more massive and massive, and then from there, if they reach a certain critical threshold, they can really start to accrete a lot of gas. So in this case, we weren't able to form them, and it's only through really dialing up the dust disk masses by an order of magnitude or two, where we can start to form these types of planets, these close-in Neptunes. And we were able to derive an occurrence rate of about 5% within the detection of this one planet within the HPF survey. And we were able to match the simulated frequency of these planets in our simulations. And LHS 3154b, then this detection is then really highlighting that the protoplanetary disk dust mass is most likely among the lowest mass stars need to be somewhat more massive than previously thought. So with that, I'll conclude with my summary slide, where I've talked about a really exciting, surprisingly massive planet around a small star, which is causing us to scratch our heads about how planet formation occurs around the very lowest mass stars. I was really excited to hear, especially Feng Wang's talk yesterday about studying the protoplanetary disks with ALMA around the very lowest mass stars. I'm looking forward to talking with her and others here that are experts in that on gaining further insight into the disks around the lowest mass stars. With that, I'm happy to take questions.
Any questions?
Your talk. I was wondering about the stellar activity. I know that you should have an incredible high resolution spectrograph, and I was curious which lines in particular you would look at.
Yeah, so that's a great question. So this star is actually exceptionally inactive, especially given how late of a star it is. Usually, the very latest stars are active; they flare a lot and things like that. This one shows no H-alpha emission, which is actually really surprising for such a low mass star. That's actually a really strong constraint on that the rotation period is long. The rotation period is most likely around 120 days. So yeah, exceptionally inactive star. That was actually really helpful also to enable the precise rate velocity observations. We also took a look at canonical activity indicators. We don't see anything there. And yeah, it's actually nicely well-behaved, slow, old star. Yeah.
All right, any last quick questions? If not, I guess we can again. So our last talk in this session will be virtual. So Fei Dai, hopefully you're online.
Yeah, I'm here.
Okay, great.
Can I
Give me
go
1
ahead
second
and share my
to stop
screen?
screen, and then you can go ahead and share yours. Okay, we can see you, so please go ahead and share your screen.
All right. How does that look?
Okay, yes, that looks good. Go ahead, I will just flash the time warnings in front of the computer. So take it away.
All right. Hi everyone, my name is Fei Dai. I'm currently a second fellow at Caltech, and I'll be joining the University of Hawaii next year as a faculty member. I am mostly an exoplanet observer interested in figuring out their composition, orbital architecture, and dynamical evolution. In this talk, I'll showcase the detailed characterization of a near-resonant planetary system, which may tell us about planet formation in general. So more than 2,000 years ago, in ancient Greece, Pythagoras noticed that two musical notes sound harmonious if their frequencies are resonant. In other words, close to some small integer ratios. And Pythagoras firmly believed that the celestial objects must also follow a harmonic relationship, giving rise to a cosmic symphony. 400 years ago, Kepler, who was heavily influenced by the Pythagorean worldview, looked very hard for resonance between the solar system planets. And you can see in his manuscript that he tried very hard to fit musical notes to the orbits of the solar system planets. Obviously, Kepler failed. We now know that the solar system, or at least the inner solar system, does not have a resonant configuration. However, it was through this obsessive search for resonance that led Kepler to discover his third law, which sparked the advent of celestial mechanics and accelerated the scientific evolution. Today, we have discovered thousands of exoplanetary systems, and this plot shows the observed pure ratio between neighboring planets from the Kepler sample. The vertical dotted lines indicate low-order resonances, such as 2-to-1, 3-to-2, etc. And most Kepler planets are not resonant, as indicated by this broad distribution of pure ratio. Only a few percent of these systems are currently near resonance, highlighted by the blue area. And if you further zoom in on the near resonance systems, they still show about 1% deviation from perfect resonance. Here, the deviation from resonance delta is simply given by the observed pure ratio between neighboring planets, divided by the closest integer ratio, P over Q, and you normalize against unity. And most planets, most near resonant planets, still show this about 1 to 2% deviation in the histogram on the right. Okay, that is observation. On the other hand, if you ask a modern planet formation theorist, they'll probably tell you that resonant planetary systems should be quite common, if not ubiquitous, at least initially. This is because planets migrate as they form in a protoplanetary disk due to the gravitational interaction between the planets and the disk. In most part of the disk, the net effect is for the planet to migrate towards the central star, and the semi-major axis decreases over time. If multiple planets are forming and migrating simultaneously, then the pure ratio between neighboring planets change continuously, and they may cross a resonance. Once the planets are near resonance, the mutual gravitational interaction between the planet gets amplified and acts as a potential well that traps planets together. And once planets get caught in this resonant lock, a pair of planets can migrate in unison towards the central star. And this process can be extended to capture several planets into a resonant chain, as shown by the schematic on the left, basically the third panel here. You can see the planets have pure ratio of 4-to-3 and a series of 3-to-2s. Indeed, a small number of resonant chain planetary systems have been discovered. I talked about one of them, TY 1136, last year. Some of these resonant chain planets may have orbital pure ratios that are extremely close to perfect resonance, highlighted by the red box here. They're almost on top of the origin here. And for the experts in the audience, their resonant angles are also in a state of libration, which is a hallmark of true resonance. However, the resonant chain systems are the minority rather than the norm of the observed planetary system. Again, only about 10 of them have been discovered. The question is, are resonant chains intrinsically rare, or are they routinely produced by planet migration, but later disrupted by dynamical evolution? Some proposed mechanisms for driving a planetary system away from resonance include tidal interaction with the host star, giant impact collision among the planets, as well as scattering by planetesimals. Over roughly 5 years of dynamical evolution, which, by the way, is the median age of the Kepler sample, these dynamical processes could disrupt any initial resonance produced by this migration. All right, with that as a context, I present a new adolescent planetary system discovered by TESS, which may be halfway through that dynamical evolution pathway. So TOI 4495 is a late F star with 2 transiting planets of orbital period of 2.6 days and 5.2 days. The period ratio is near 2:1 mean motion resonance with a deviation right about 1%. So right in the middle of the histogram here. So with 1% deviation from resonance, the resonant interaction is still strong enough that we detect a strong transit timing variation on both planets with the amplitude of about an hour. The plot on the right shows the TESS observation of the system. Using various age indicators, including isochrones, gyrochronology, and lithium absorption, our best age estimate is about 1.8 years or so for this system. With such an age, the system is also intriguing from a mass loss perspective. In particular, X-ray and UV-driven fluid evaporation should have more or less concluded, since the high energy radiation from the host star dwindles after the first few 100 million years. And here are the masses and radii of the 2 planets, along with theoretical mass radius curves. It looks like that the inner planets on 2.6-day orbit has lost substantial amount of any primordial hydrogen-helium envelope. It is now a mini Neptune of just 2.7 Earth radius, with about 1% of its mass in a residual hydrogen-helium envelope. On the other hand, the outer planet, which is on a 5-day orbit, seems to still manage to hold on to its hemisphere, requiring about 10% of its mass in a hydrogen-helium envelope. The much heavier core of the outer planet, perhaps larger than 20 Earth masses, was instrumental for suppressing photo evaporation on that planet. So we further constrained the dynamical state of the system by measuring the stellar obliquity, which is how misaligned the orbital plane of a planet is relative to the equatorial plane of the host star. And the large misalignment is usually a signpost of a dynamically violent evolution that tilted the orbit of the planet. So to illustrate how stellar obliquity can be measured using high-resolution spectroscopy, let's look at this movie made by George Zhou. So if you look at the bottom right panel, here we are seeing the surface of the star. Due to the rotation of the star, half of the star appears to be blue shifted and the other half is red shifted. And the upper panel shows the resultant line profile if you integrate the whole stellar surface, again, dividing into the blue shifted and red shifted part. And by analyzing the shadow cast by a transiting planet, we can determine the orientation of that planet relative to the star's rotation pattern. And in this particular case, we can see the planet only blocks the blue shifted part of the star, thereby telling us its orbit must be misaligned relative to the star. So thanks to the recently commissioned Keck Planet Finder, which is one of the most advanced, most capable optical spectrograph ever built, we were able to measure the stellar obliquity of the system using both the more traditional Rossiter-McLaughlin effect, shown in the middle, and the distortion of the line profile that we just talked about. I would like to highlight that the amplitude of the signals are respectively only 3 meters per second and 400 ppm in terms of line profile distortion. So this is one of the most exquisite stellar obliquity measurement carried out so far. Using either technique, we found a well-aligned coplanar orbital architecture for this system. The misalignment is no more than a few degrees, which reveals a dynamically quiet evolution history for this system, one that probably does not involve a violent event such as giant impact collision. The most commonly invoked explanation for the deviation from resonance is tidal interaction with the host star, also called resonant repulsion. In this case, the energy of the planet gets damped by tides, and the pure ratio of a resonant pair will slowly deviate from perfect resonance, basically moving the planet from deep in resonance to that 1 to 2% deviation. So now going to the equations, I'll just note that the characteristic behavior of resonant repulsion is that the pure ratio, delta, should deviate as time raised to the 1/3 power. And the bottom panel actually shows our data embodied simulation, and this theoretical behavior is recovered very well. So one can compare the rates of resonant repulsion, the age of the system, and the currently observed depth of resonance. And with that, we can constrain the amount of tidal damping that the system has sustained. If we do that exercise, the implied tidal quality factor Q prime on the inner planet is surprisingly low, actually smaller than 1200 or so. This is quite similar to our Mars. However, the planet clearly bears more resemblance to our Neptune with the thick hydrogen helium envelope. Its tidal quality factor of a Neptune-sized planet should have been closer to the 10 to the 4th level. So this is a well-known problem with resonant repulsion. The required tidal dissipation is usually much stronger than what is observed for the solar system planets. Obliquity tides may offer some help, but does not fully resolve the problem. A simple solution was recently proposed by both Choksi and Chen, as well as Goldberg and Bedigan. In contrast to previous simulations, where the planet migration was carried out in a polar planet disk that is very smooth, i.e. with no turbulence. These new works relaxed those assumptions and allowed turbulence in the polar planetary disk, which is shown in the middle. The stochastic forcing by turbulence could have deposited pairs of planets rather wide of resonance. In other words, near resonance systems like TOI 4495 could have started quite far off from resonance with about 1% deviation. And the two panels on the right shows the direct simulation from Goldberg and Bedigan. Here we can see that by allowing turbulence in the disk, resonant pairs show a range, a rather wide range of delta, or the deviation from resonance, as well as a non-zero eccentricity initially. For TOI 4495, we put the system on the same diagram here, and you can see that this new system we're talking about here are rather consistent with the prediction of migration in a turbulent disk. All right, with that, I'll end here, and I'll quickly say that Pythagoras and Kepler may rejoice at the knowledge of resonant planetary system out there in our galaxy, just as they had envisioned, but they should be even happier that there are actually some underlying physical mechanism that are responsible for crafting such resonant configuration without relying on some sort of grand design. All right, I'll end here and take any questions.
Do you have any questions? I'm not sure. Can you hear this mic?
I think, can you hear me?
Yep, go ahead.
Yeah, really great talk. This is Guðmundur. I don't know if you can see it, but really great talk. I was just wondering, do you see any signatures of any other planets in this?
Sorry, I was losing you a bit towards the end.
Do you see any signatures of other planets in the system?
Yeah, so we actually only have TTV mass measurements. The star is pretty active, or I would say the V sign is pretty high at about 8 kilometers per second. So the star is really not quite amenable for long-term radial velocity monitoring.
I see.
So yeah, we don't have any constraint on longer period plan at the moment.
May I ask quick questions? If not, let's thank our speaker and all the speakers from this session.